KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, this is second class from the chapter Dual Nature of Light. So it is a second Neet class from the chapter Dual Nature of Light. See here, yesterday we discussed that, in our previous class, we focused and we discussed what is work function or threshold energy, right? Afterwards, we went to discuss photoelectric effect. Then we discussed some of the important points regarding the photoelectric effect in the case of experimental setup. Okay, right. So I will repeat once again what we discussed in our previous class briefly. What is meant by work function or threshold energy, right? It is the minimum energy of incident radiation required to eject the electrons from metallic surface, right? Work function is the minimum energy of incident radiation required to eject the electrons from metallic surface, from a particular metallic surface, because we have different metals, right? So it is different for different metallic surfaces. So that's why here the point is the minimum energy of incident radiation required to eject the electrons from metallic surface is defined as work function of that surface. Okay, right. So now I am repeating these many times means you identify the importance of definition. Okay, right. Next, what is photoelectric effect? The phenomenon of emission of electrons from a metallic surface when illuminated by light of appropriate wavelength or frequency is known as the photoelectric effect. Okay, that's what is meant by photoelectric effect. Next, we start to discuss about the things from this class. Okay, right. So in our previous class, two important things. One is work function, another one is photoelectric effect, and some of the important points we also discussed in case of photoelectric effect. So nearly 6 points we discussed. Okay, right. Now, in this class, the first one is threshold frequency. Okay. So if you observe carefully, when a metallic surface is exposed to the electromagnetic radiation, then emission of electrons will take place. This is what it is, the phenomena of photoelectric effect. But now immediately we have to discuss, we have a lot of doubts and we have different ideas. That is what amount of frequency of incident light is needed, what amount of wavelength of incident light needed, right? And what is the energy of the incident light? Okay, so these are all important. These are all important, because how can you say that, suppose for example a light of very low frequency incident, what happens to the photoelectrons, right? Suppose a light of high wavelength or otherwise very low wavelength incident, what happens, right? So So these are all simply called as consequences, right? So the different things regarding one natural phenomena, right? So that is the main important discussion. In our Neet point of view, every concept we have to see in multi-dimension, in multi-direction, right? Not learning and reproducing, right? That is not work out here. So every concept and every statement you have to see from many directions, right? See here. First, what is threshold frequency? See here. The minimum frequency of incident radiations, the minimum frequency of incident radiations required to eject the electron from metal surface. The minimum frequency of incident radiation required to eject the electron from metal surface is defined as threshold frequency, right? So it is what it's giving a limit of frequency, right? It is giving a limit of frequency. That is what he is saying. The minimum frequency, right? The minimum frequency of incident radiations required to eject the electron from metal surface is defined as threshold frequency. Is defined as threshold frequency. Okay, right. See here. If incident frequency nu is less than nu naught, if incident frequency nu is less than nu naught, no photoelectron emission, right? So what he is saying, suppose for incident radiation, if the frequency is less than minimum frequency, that is what, less than threshold frequency, less than threshold frequency, what will happen? No photoelectron emission, no photoelectron emission. Okay, right. And see here, for most metals the threshold frequency is in the UV region, that is what, ultraviolet region. So corresponding to wavelength between 200 and 300, that is what, 200 and 300 millimeters, right? Corresponding to the wavelength between 200 and 300 millimeters, right? See here, what I am saying is, for most metals the threshold frequency is in the ultraviolet region, corresponding to wavelength between 200 and 300 millimeters, right? Okay, so this is what range you just see for exact value, right? In our chapter electromagnetic waves, we had a table, that is what wavelength of one particular region, either ultraviolet region or infrared region, whatever it may be. Okay, right. See this next. But for potassium and cesium oxides, it is in the visible spectrum. But for potassium and cesium oxides, it is in the visible spectrum. That is what, wavelength between 400 and 700 nanometer. 400 and 700 nanometers, right? So I will repeat once again this information. For most metals, the threshold frequency is in the ultraviolet region, but for potassium and cesium oxides, it is in the visible spectrum. Okay, right. I hope you understood what is threshold frequency. It is as simple as such. To raise the discussion of what is threshold frequency, the basic doubt is, what amount of frequency of incident light is required to emit the electrons, which is photoelectric effect. The question is, we have to think, right? So based on that we can answer, that is what, there is a requirement of certain minimum frequency of incident radiation for photoelectric effect. So that minimum frequency of incident radiation required to eject the electron, from metal surface, is defined as threshold frequency, okay, right. Afterwards, if you observe carefully, see here, just it is just like an expression or a mathematical equation like that, just a small thing. If incident frequency nu is less than nu naught means, I already told you, no photoelectron emission, okay. Afterwards, it is most of the metals, the threshold frequency is in the ultraviolet region corresponding to the wavelength between this value, that is what 10 nanometers to 400 nanometers. But for potassium and cesium oxides, it is in the visible spectrum, that is what wavelength is between 400 to 700 nanometers, otherwise 400 and 700 nanometers, in between that range, okay, right. And next threshold wavelength, see here. So what is the threshold wavelength? Observe carefully, just based on this you can understand, that is what if incident wavelength lambda is greater than the threshold wavelength, then you cannot expect any photoelectrons, that is what no photoelectron emission, right. If incident wavelength lambda is greater than lambda naught, no photoelectron emission. Next, see that Hedge observations, right? Hedge observations. See here. The Hedge is the name of the scientist, no? So he has yesterday also we discussed the hard work, right? The work done by Hedge, hall work, right? So they had a certain amount of work, and that is also valuable in case of photoelectric effect. That is what in the chapter of DL nature of lights. Okay, see this. That I am going to explain now. Hedge observations. The photoelectric phenomenon was discovered in 1887 by Heinrich Hedge during his electromagnetic wave experiments. Right. In his experimental investigation on the production of electromagnetic waves, by means of spark discharge, Hedge observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp, right. So it is a very basic information, so how we could find this natural phenomena, and what happens, right, what happens in case of experiments done by Hedge, right. So the basic information we are in a discussion, right. Okay, see, observe carefully here. The photoelectric phenomenon was discovered in 1887 by Heinrich Hedge during his electromagnetic wave experiments, full stop. In his experimental investigation on the production of electromagnetic waves, by means of spark discharge, Hedge observed that high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Okay, right. So what I am saying is here, yesterday I drew one picture which was showing experimental setup. Okay, so there I told you what is discharge tube, right, and afterwards how the electrons are emitting from the emitter plate when that emitter plate is going to illuminated by ultraviolet light or electromagnetic wave, that is what electromagnetic wave, right. So yesterday I told you in that picture, and there itself we were discussing how the electrons are emitting just like experiments. Okay, so the same thing here he is saying, but here he is saying that this is what, observe carefully, high voltage sparks across the detector loop were enhanced when the emitter plate was illuminated by ultraviolet light from an arc lamp. Next, see this. When light falls on a metal surface, some electrons near the surface absorb energy, but enough energy from the incident radiation to overcome the attraction of the positive ions, in the material of the surface, material of the surface, right? So when a light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of positive ions in the material of the surface. You please understand, see here, in a metal surface, right, so the electrons are basically negative, positive charges are also present, positive ions are also present, okay, right. So when these electrons trying to come out from the metal, when the metal surface is going to expose to the light, the positive ions will try to pull the electrons back, okay. When the positive ions try to pull the back, the electrons cannot come out from the metallic surface, right. So here the attractive force by the positive charges or positive ions for negative charges, which are electrons, should overcome. To overcome this, to overcome this barrier, or to overcome this attractive force by the to overcome this attractive force for the electrons by the positive ions, these electrons need certain amount of energy. That energy should sufficient, otherwise electrons will not come out. If the electrons will not come out, that is not our discussion. Our discussion is the ejecting of electrons from a metallic surface when the metallic surface is going to expose to the light, okay. That only he is saying here. I underlined this word, these all the things, right. See here, when a light falls on a metal surface, some electrons near the surface absorb enough energy from the incident radiation to overcome the attraction of the positive ions in the material of the surface, okay, right. Next, see this. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space, right. He is telling after that what will happen. After gaining sufficient energy from the incident light, the electrons escape from the surface of the metal into the surrounding space, right. So whatever the space which is present surroundings to the metal. Next, the next thing, that is what Hallmark's and Leonard's observations. Hallmark's and Leonard's observations means what? No, when they are doing some experiment, right? Sometimes when we are doing some experiment, our intention is one, and when we are going to achieve that intention or our aim, meanwhile we may get that is what some of the accidental things, right. So that is what this is the very common thing sometimes, okay, not all the times, right. So similarly here, Hallmark's and Leonard's observations means when they are doing the experiment, right, so what they observed, see here, Leonard, the period is 1862 to 1947. Leonard observed that when ultraviolet radiations were allowed to fall on the emitter plate on an evacuated glass tube, enclosing two electrodes, that is what electrodes are nothing but metal plates. See how we are having electrodes, positive electrode and negative electrode in our battery, it is what cell, okay. So similar to that, current flows in the circuit, right. So he is saying that, Leonard observed that when ultraviolet radiations were allowed to fall on the emitter plate on an evacuated glass tube enclosing two electrodes, current flows in the circuit, okay. That is what he is saying. Next, as soon as the ultraviolet radiations were stopped, the current flow also stopped, right. As soon as the ultraviolet radiations were stopped, the current flow also stopped. These observations indicate that when ultraviolet radiations fall on the emitter plate, electrons are ejected from it. So what is the final conclusion because of these things? You know, when ultraviolet radiations fall on the emitter plate, electrons are ejected from it. These electrons are attracted towards the positive collector plate. You know, electron is basically negative charge, and just opposite to that, right? On the other side, we had a negative electrode, a positive electrode. That is what we are calling it as collector plate, because the electrons are moving towards the collector, right? So which collects the electron. That's why it is called as collector plate, right? So it is a positive collector plate, full stop. Thus, light falling on the surface of the emitter causes current in the external circuit. Causes current in the external circuit, right? So you please keep in mind. We connected yesterday. I showed you one picture. You know, in that picture, I connected the two electrodes which are acting like emitter and collector to a battery, right, to create some potential difference. That's all, right? But that battery is not our discussion to get the current in the circuit. But what is our discussion to get the current in the circuit? That is what as photo current. That is the converting energy from light energy into electrical energy. Light energy into electrical energy, right? That is our discussion. See here. Thus, light falling on the surface of the emitter causes current in the external circuit. Causes current in the external circuit. Okay, right, full stop. Hallworks and Leonard studied the variation of photocurrent with collector plate potential. Hallworks and Leonard studied the variation of photocurrent. Hallworks and Leonard studied the variation of photocurrent with collector plate potential and with frequency and intensity of incident light, right? So this is the important point. So for our Neet point of view, we have to see the concept in this way. That is what see here, variation of photocurrent with collector plate potential and with frequency and intensity of incident light. Okay, so that is important for us for Neet point of view. Okay, see here next. In 1888, Hallwork connected a negatively charged zinc plate to an electroscope. He observed that the zinc plate lost its charge. He observed that the zinc plate lost its charge, right? So which is basically negatively charged plate, it is basically negatively charged plate which is to an electroscope, but he observed that zinc plate lost its charge when it was illuminated by ultraviolet light. So he connected zinc plate which is negatively charged. It is going to expose to the ultraviolet light. Then what will happen? The electrons are coming from that. So when the electrons are coming from that, what happens? It lost its negative charge, no? Right? That's what he is saying. Next, see this. Further, he connected, that is what, uncharged zinc plate. Further, the uncharged zinc plate become positively charged. Further, the uncharged zinc plate become positively charged zinc plate, right? It was, okay, see here, positively charged. When further the uncharged zinc plate become positively charged when it was irradiated by ultraviolet light, right? So see the difference between these two. When the negatively charged zinc plate exposed to the ultraviolet light means it loses its negative charge, right? When neutral, that is what, uncharged zinc plate can expose to the ultraviolet light means it becomes positively charged. So based on these two things, what is our idea? What is our conclusion? Right? So it is what? It emits electrons. Okay? That is what generally you can understand. Next, see here. Positive charge on a positively charged zinc plate, positive charge on a positively charged zinc plate was observed to be further enhanced when it was illuminated by ultraviolet light. So, when it continues to expose to the ultraviolet light, he observed that the positivity of plate is going to increase. From these observations, Hallworks concluded that negatively charged particles were emitted from the zinc plate under the action of ultraviolet lights. Okay, before getting this information, even they could not name them. We are calling them as electrons, okay. But you see here, he concluded that the negatively charged particles were emitted from the zinc plate under the action of ultraviolet lights. Okay, right. Next, see here. It is what Hallworks, and one more point I will tell you, because of insufficient space I didn't write. I will tell you one point before this. Right? See this. After the discovery of the electron in 1897, it became clear that incident light causes electrons to be emitted from the emitter plates. Right? Okay. Next, due to negative charge, the emitted electrons are pushed towards the collector plate by the electric field. Very well, that is what positive charge attracts to the negative charge, or negative charge attracts to the positive charge. Okay, right. Next, see here. Hallworks and Leonard observed that when ultraviolet light fell on the emitter plate, no electrons were emitted when the frequency of the incident light was smaller than a certain minimum value called threshold frequency. Right? The starting of this class I told you what is threshold frequency. Once again he is saying that is what he observed while doing the experiments. Okay, that is what. This threshold frequency or minimum frequency depends upon the nature of the material of the emitter plates. I will repeat once again the last point, which is important for Neet. The minimum frequency or threshold frequency depends upon the nature of the material of the emitter plate. Okay, right. So, in this class, we discussed what is threshold frequency and what is threshold wavelength. Afterwards, what are the Hedge observations and what are the Hallworks and Leonard observations. Right? These observations, either Hedge observations or Hallworks and Leonard's observations, are giving a complete information about this idea of photoelectric effect and some of the relations also. For example, the idea of threshold frequency, right? So, the basic information, that is what regarding the birth of this idea of photoelectric effect, and afterwards some of the relations. For example, what is the relation of photocurrent to the intensity of incident radiation and frequency of incident radiation and wavelength of incident radiation, right? So, these are all we discussed. Okay, right. So, in our next class we will continue this topic. Okay, thank you.